All right, there we go. Okay, so the topic for the next two lectures will be epidemics. We'll talk about epidemics spread on networks. And before we do that, we will need to learn some theory, some fundamentals on how to deal with these types of models. Now, I think at this moment, there is really no need to motivate this type of study or this topic. So let's just jump into it right away. In fact, I prepared the slides, almost a year ago, actually probably precisely a year ago, when the COVID was just starting around the world, and so we knew what this is going to be. What you see here are the numbers that everybody was monitoring back then. For example, if you notice, it's China, Iran, France, Korea, and this, what we see on the x-axis, this is the number of cases, COVID cases, and on the y-axis, it's time axis. Now, it's been designed such a way that we shifted, the time is shifted such a way that epidemics start date matches for different countries. So of course the start dates were different. All right. And so on the left-hand side, you see the progression of epidemics in different countries, right? In France, US, Iran, China. This is in total numbers, right? 5 days, 10 days, 15 days, 20 days after the start of noticeable epidemics, and the start here is considered, I believe, like 100 cases. Now, this is also the same type of data, but now it's for Spain, Germany, France, Switzerland, Netherlands. Again, you might notice very, very similar behavior. So it doesn't matter what country is, but at the function of time, the number of infected people growing really, really fast. And in fact, it's exponential growth. Now, how do we know that it's exponential growth? Well, take a look on the right-hand side. What you're going to see here is it's the same picture as on the left, except for the y-axis is logarithmic, right? Now, let's take a closer look at this. Zoom in. You realize that when it is a logarithmic axis, all the curves, well, look more or less like a straight line, and they lay on along the same line. Maybe there are two different slopes here. For Italy, you notice that the slope started at a certain angle and then reduced a little bit. But now, what does this really mean? Why do we say that this is exponential growth? Well, if you just think about this for a sec, now this is a logarithmic plot, right? And so here it means on the exercise on the x. Wait a minute. Why is it not letting me draw? Hold on a second, guys. Something strange. By some reason, I cannot annotate anymore here. All right. Well. That's sad. So let me try one more time. Well, I guess there was some update on the software, and now it doesn't allow me to draw. Well, okay. So if you think about this, then oh, now it's working. Amazing. All right. So what you have on the left-hand side, on the y-axis, it is logarithmic axis, and so we have logarithm y And on the right-hand side, we get a straight line, right? And so if it's a straight line, well, you can call it AX plus B, right? That's the equation of the straight line. So that instantly means that Y is exponent to the power AX plus B, or we can put it whatever coefficient, CEA X, right? If X is a time and Y is a number of cases, so we get that number of cases as a function of time is some number of cases when time was 0, E, some coefficient, some rate times time, okay? Or you can write it N0, some, I call it R here, to the power of T. Okay, so which means on every time step, the number of infected cases increases by R, and that's exponential growth. And so that's why we talk here about exponential growth rate of infection. Okay. All right. So if we think about like the most simplistic possible model here, that sort of naive model, but that the model explains this growth is the following. So you guys, so many people are late. Come on. Okay. So the simplest model. So we have some number of people, like the sort of first wave of infected people. It can be just one person. On average, it meets some other people, and there is certain probability with which during this interaction, the disease transferred and the person getting sick. So if somebody meets on average K people during the time the person is contagious, and then the transmission probability is P, then on average, this person will make P times K average people sick. All right. So, then each person out of those new sick people, right, the second wave will meet new people and infect those, and so on and so forth. And that will continue until, of course, the infection sort of runs out of steam, runs out of people it can infect. Now, for this process, it's it's actually, there is a name. It's called Galton-Watson branching process, and can describe by the following tree, right? The branching tree. So here it's it's a coefficient 3, but we understand that on average it's P, the probability of the transmission, and times K, average number of secondary infection from one person, from one node. And some of those branches can stop if, again, this is a probabilistic, and there might be some person who will not infect anybody, or it can grow. It can grow quite deep. And if you think about this model, let's take this P times K average. And this will be the average number of new infected people on every step, right? Or for a person during the time he is infected. Then we call it R0. And so after n steps, or n time steps, the number of infected people will be this R0 to the power of n, or P K average to the power of n. So it's pretty much what we just assumed and draw on that line, right, on the picture we had. And then if it's sort of obvious, right, that if we take this progression, right, so it is P average K to the power of n, right, and if this P times K average is less than 1, then whenever we take it to the power, it's getting smaller and smaller, right? Becomes 0. But it's also quite natural to understand that, yes, if on average a single person infects less than one person, then eventually disease stops. Now, if it is greater than 1, then you get this multiplication factor, and it grows geometrically fast. Now, geometric growth within the integers is exponential growth when time is continuous. And this number R0, we're going to see it a lot. We're going to meet it a lot. This number is called, so this number is called basic reproduction number. And so it's average number of secondary infection produced when one infected individual is introduced into the population, where all the people are susceptible, right? So they can be infected. And even within the simplest model, it's very clear that the threshold is R0 equal to 1, right? So when you get greater than 1, then on average person infects more than one person, and so the disease will spread. And if it is less than 1, then eventually disease will stop, right? But we're going to see this R0 further in the computations that will come up naturally within our further models. Okay, so that was that's the basic idea for this branching process. Now this R0, this rate of reproduction number for different diseases is different, and like measles or pertussis, these are like very, very contagious, and the reproduction number is 12, right? So on average, every person kind of infects 12 people. For influenza, it is 2 to 3. Do you guys know what the R0 is for COVID? So R0, of course, changes depending on all the measures that are being introduced, right? The masks and isolation, and of course, the weather patterns, etc., etc., etc. Yes, so it changes with time, but on average, yes, it is around measured as being 2 or 3. So it's quite close to traditional typical influenza rate. So it is infectious, but it is not as crazy infections as measles, for example. Okay. Now, the study of the spread of infection, it's epidemiology, and in fact, the basics, the fundamental model goes back to like 1927. And it has been presented by Kermack and McKendrick, and it's called Compartmental model. And so the idea in that model that you have different classes of population, and every class of population can connect, can mix freely with other classes of population, and it's called fully mixing model. It is closed population model in the sense that there is no new people being born. There is no migration. There is nothing like that. So these are classes of population. And one class is a class of susceptible people. So those people who can get infected. The second class is a class of infected people. So those that have disease and are capable of spreading the disease. And the third class is usually called RFT, which is a recovered people. These are, those are either recovered from the disease or and cannot transmit anymore, or sometimes it's removed, which means they died from the disease and they're also not considered. So a person can, so those classes, right? So a person can typically start within the class S, right? So a person typically will be susceptible to the disease unless, for example, a person is immune, vaccinated. Then the person becomes infected, and then goes into the stage R. And so, depending on how we consider those, how many classes we consider, how many compartments we consider, and how people are moved from those compartments, there exist multiple models. There is SI, SIS, SIR, SEIR, like many more. We'll look at those models today. All of them are pretty much differential equations. Those models, they become differential equations from a mathematical point of view, and we can actually solve this. So we can see how the number of people within each class evolve with time. So how number of susceptible people decreases, how a number of infected people increases, and then decreases, et cetera, right? So what we're going to do within those models is we're not monitoring individual person, but we're monitoring groups of people that have certain properties, like groups of susceptible people, group of infected, and group of recovered people. And then we monitor the number of people within that group. And then that number it will be modeled through differential equations, and then we'll change the function of time. Okay, does this make sense? You guys quiet today. Okay, so we're going to start with the simplest basic model. It's also called SI model. So within this model, there are two classes. There is a class of susceptible people, there are a class of infected people. And at the beginning, you have maybe one infected person. Most of the people are within a susceptible kind of world. If I take this as population, actually, let me clear this. So at the beginning, so we have this is susceptible, that's infected, and there is probably one infected person, then infects more in susceptible. So as time goes by, we get less susceptible, more infected, and then eventually, say in this model, we'll get only all infected people. So we're going to observe right now how this works from the numerical point of view. So again, we have a class susceptible, class of infected, and the susceptible person can become infected. So can kind of move from susceptible to infected class. But the total number of people, of course, is conserved. So S of t plus I of t is n. Now, we're going to introduce what we called transmission or infection rate, or number of transmitting contacts per unit time. Whatever unit time we choose, we can talk about a day as a unit time, or we can talk about an hour, a minute, a second. So it's number of transmitting contacts. Now, what does it mean? It means the contact when the transmission happened. So it's not just the number of contacts, but it's a number of contacts when the transmission is actually happened. So on average, this can be number of contacts times the probability of transmission. You can also think about this. You can also can imagine this as 1 over beta is time between transmitting contact. Now, here is the differential equation. So the number of infected people increases with time. Why, how does it increase? Well, we have a number of infected people at the beginning, right? There is, one person, or how many people where they are infected. Then infection happens when infected person meets susceptible person, and then transmission happens. So the way we calculate this is I of t times the probability of meeting meeting a susceptible person, and this is a fraction of susceptible people, times the probability of the transmission at that moment. So then we can just take this and instantly write it as a differential equation, right? Take this difference, write it as a differential equation, and this is what we have, right? Di dt beta S of t I of t. Now, it is very clear, even from this equation, that di of t, this is a derivative, right? It's derivative of I, of infected people. On the right-hand side, we have only positive numbers. Number of susceptible people, no negative, right? Number of susceptible is greater than 0 until it becomes 0, right? Number of infected greater than 0. So this is greater or equal to 0. So which means I will be always increasing until it kind of stops increasing. But within this formulation, it will never decrease. So we can predict that the shape of I as a function of t, even without solving equation, it will probably go somehow up and then saturates when there is no more people to infect. But that's purely conceptually right now. We're going to see how we can actually analyze this equation. In fact, this one we can just solve precisely. So let's do it. It's actually easier to work, instead of working with total number of infected or susceptible people, it's easier to work with relative numbers, so with fractions. So put here fractions, then we can instantly write the equations like this, right? It's the same equation as in the previous slide, but we just divide it by n. And then, since it's again the fractions, the sum has to be equal to 1. The next step, what we're going to do is, we're going to, this is so this is a differential equation, and this is a constraint. So what we're going to do is we're going to express, for example, s from this constraint and plug it in here. So then we get a differential equation, and as any differential equation, we need to have it's time dependent. We need to have a boundary, or actually initial conditions in here. It's time, and so initial condition, what's happening at time equals 0, is going to be I0 infected people. So now this is a differential equation, and we can just take it and solve it. And the solution is actually can be done by separating of variables. If you don't remember, what you do is you take this, move it to the left, dt to the right, and integrate. Okay. So when it's done, this is what we get. That's the function. That's the function that describes number of the fraction of infected people as a function of time. If we want total number of infected people, we just need to take this I and multiply it by n, right, by the total number of population. But the fraction goes from small to 1. Now that was the initial number of people. This is just sort of a simulation, and eventually it gets to 1. If you look at this equation, you realize that when time goes to infinity, right, when time is large, this term goes to 0, and then I of t becomes equal to 1. So which really means the following. When you have this type of model, when there is only one process that susceptible person becomes infected person, and there is no sort of recovery, the obvious result is eventually everybody will get sick, right? And it's just a matter of time, and pretty much the only interesting part here is how this curve, what the curve looks like. If it is this way, or whether it is this way, or maybe this way, or maybe this way, right? And we know from the equation right now, for this particular, with beta, this is an S-shaped curve, right? So at the beginning, you get this accelerated, quite accelerated. And by the way, this is very important, what we get here, that there is this acceleration, and then there is some slowdown, and then eventually the disease runs out of fuel, runs out of people. But what's important is when time is small, when we are here, when time is small, this process really goes, if you look at this equation, I0 is small, so this behaves as E beta T. And remember what we started lecture with, that's pretty much that behavior, that performance is just this equation reproduces the results we saw in sort of on a experimental on the real world data and in our very, very simple branching process model. Okay, but it would make a lot of sense to just introduce differential equations and limit ourselves to this very simple case. So let's look into more interesting, more complicated models, more complex models. So the next model I want to look at is called SIS model, and it is SIS because there are two transitions possible. So a person can get infected, and then person recovers. So in some sense, you can also draw this as from susceptible someone becomes infected, but then it can recover and become susceptible again, right? So it's sort of, this model works, for example, for seasonal flu, where you can actually get, get sick several times in a season. So, but then you recover. So for this model, there are really two transition rates, right? Transition rate, which is going from susceptible to infected, right? So the infection rate, but then there is also recovery rate, right? Which is recovery rate. You can think about the inverse of the recovery rate as an average time to recover. Okay. So again, beta, usually interpretation is on average on single time step, how much, on how many people are getting infected, and gamma interpretation usually is the inverse of gamma is time to recovery. So if, it takes 5 days to recover, okay, gamma is 1/5. So then the infection equations actually becomes a little bit more complicated. So what happens is the following. If we take susceptible people, those that can get infected, then the number of susceptible people will decrease due to people getting infected, right? And the rate is, again, there is this I, number of infected, because in order to get infected, somebody needs to be in contact with infected person. Beta, the rate of transmission, and the number of susceptible people, right? The more susceptible people are there, the more chances they get infected. It's the same as as equation for the SI model. But what we also get here is a new term, which is gamma I, because now, on one hand, the number of susceptible people decreases due to them getting infected, but then it increases due to people recovering, right? So here is, beta, here is gamma. If we want, we can write the similar equation for number of infected people. The number of infected people is growing due to the infection propagation, due to infection spread, right? Due to the fact that susceptible people becoming infected, but decreasing because they recover. And again, there is only two classes, so susceptible and infected, and they add up to 1. So again, we're looking to the differential equation, initial condition, substitute constraints in, that's what we get. The equation looks slightly different. Let's see how we can solve it. So, we can also solve this equation exactly, precisely, and here is a solution we get. Now, let me, for a second, go back to the solution of the previous equation, right, on the SI model. Notice that, yes. Okay. Notice that here we had only coefficient beta, right, and that the coefficient that determined the slope of the curve, and that was it. Now, if we go to the new model, to SIS model, now we have two driving forces here. We have the disease, and then we have a recovery. And so instead of one coefficient, we have here two coefficients. We have beta minus gamma. And then the behavior of this model, of this equation, really depends on the relative values of beta and gamma. Remember, both of them are positive numbers. Now, if we look at this solution, if beta is greater than gamma, right? If beta is greater than gamma, so then this difference is greater than 0. And when time goes to infinity, this goes to 0. And overall, the number of infected people goes to this limit, 1 minus ratio of gamma to beta. Now, what happens when the intensity of infections are larger than the recovery rate, when the rate of infections is larger than recovery. When the rate of infections is less than recovery, so recovery happens more frequent than we get new infected people, then you can easily see that if beta is less than gamma, this beta less than gamma, this is negative. Again, negative together becomes positive. Time goes to infinity, so this whole thing goes to 0. So the answer is literally the limit when after a long time, what happens, there are two options. If beta is greater than gamma, then we do have leftover continuously persistent infection within the population. If beta is less than gamma, the infection dies out eventually. So what does this mean? Well, this means again that the infection persists within population. There are people getting recovered, right, and new people getting sick, but the ratio of the number of recovered and sick people stays constant as time goes by and goes to this limit. It's easier to see on a slide here. Again, when beta then greater than gamma, then then we eventually get constant number of constant ratio of infected towards recovered people. When beta is less than gamma, disease goes away and the entire population becomes healthy. Okay, so so within this model, it's really the interplay between those two coefficients: how fast the disease propagates, so how many people get sick every day versus how many people recovers every day. And if you get more people sick every day than recovers, then you get this one situation. Other way around, you get full recovery in the population. But what's interesting, even if you get more people sick in one day than number of recovered people, eventually it's not all the populations that continuously sick. It's some percentage of population that's continuously that always sick, and it is 1 minus gamma over beta, right? Does this make sense? I can hear you guys, but all right. Moving along. So one more model I want to look at is SIR model. And in fact, SIR model, that's the model that's usually considered more practical and used in some computations. I wanted just to build up our experience with this before jumping into this model. So again, now we have 3 classes instead of 2 classes. We have susceptible person, then becomes infected, then recovered. So it's again one-way street from susceptible to infected to recovered. We also get the coefficients beta, which is the infection rate, and then gamma, which is the recovery rate. The only thing is this R people, they cannot go back to susceptible. So for example, this when the people getting immune after, for example, they were sick with some disease, and that's what sort of happens with COVID, well, at least for a while. Now, we can write down three equations. So with susceptible people, the number of susceptible people will decrease during to infection, right? They can get infected. It's exactly the same equation on as on previous slides. Number of infected people, it's growing due to new infections, right? That comes from susceptible people. That's why they're susceptible and infected. But it decreases due to recovery. And the number of recovered people increases due to recovered infected people. So these are 3 equations. Again, system of differential equations. Unfortunately, with this system, you just cannot solve it right away, right? You cannot analytically solve it. We can sort of massage the system in the following way. We can rewrite, we can do some substitution, and actually write, some dependencies. For example, we can write number of susceptible people as a function of number of recovered people, but not, as a function of time. And then we can, for example, substitute it into another equation, and we can, write solution in this universal form. But unfortunately, we cannot take this integral analytically. So we just need to explore then the solutions numerically, or we can look at the certain limits. So if we model this numerically, that's the solution of this system of differential equations, we can get the following behavior. Now, the picture you see here is the ratio of, is selected for the ratio beta over gamma is equal to 4, right? So we kind of, the intensity of people getting sick is 4 times larger than intensity of recovery. And then there is, 0.1, I0 is 0.1, so which is, 10% population were sick at the beginning. Now, I intentionally have not labeled the lines, what's what in here. Can you guess which line means what?
Blue one is recovered, red is infected, and green is sustained.
It's susceptible. Yes, you're absolutely correct. So this line, the green line, this is susceptible people, right? And at the beginning, we had pretty much all populations susceptible, and it drops. Blue line is recovered people or removed people. So those that were sick and then recovered. So, I mean, the transition eventually gets them there. And red is the curve that corresponds to infected people. And, again, we all lived through COVID for a year, right? And you realize that, yes, that's the wave we do see a lot, right? So the number of affected growing, reaches some maximum, then start dropping. Now, what we have with COVID right now, there is like multiple waves, but there are some reasons for that, and we're going to talk about it next time. But in this simple model, this is what's happening. And in fact, why this model is useful and interesting, within this model, you can actually calculate when the maximum is going to happen, right? And you can calculate the height of the maximum. And that can allow you to predict the requirements for, number of beds in the hospitals, et cetera, et cetera, et cetera. And, you probably heard this flatten the curve slogan saying that actually means we want to, we cannot get rid of this red curve, but at least we can make it, say, flatter, right? So maybe it's the same number of people that gets infected, but it kind of happens slower. And so there is a sort of less peak on this picture. Okay, so that's sort of one scenario, right? And this is a scenario when, the infection progresses faster than people do recover, right? But then there is another scenario, another model, where the recovery is actually quicker. The recovery rate is higher than, for example, infection rate. Then you get a very different picture. In this case, like in the previous case, pretty much the way it looks like here, almost everybody was, got sick and eventually, well, recovered or removed. In this scenario, you don't get a peak on the infection. What happens is there is some number of infected people, and then just infection dies out, right? Yes, there are some other people who get, so infection dies out in the sense that the rate of infection slowing down. We get more infected people with time, but it never reaches sort of the whole thing, right? And then, yes, we got some number of people that, we first had the entire population. Now it's 80%. So it means that only 20% got sick. Again, the key difference here on the red line on the number of infected people, we didn't get a peak, all right, compared to the previous slide. Okay. Now, it's sort of intuitive. You can probably guess that sort of what's the separation, right, in between those two behaviors. But let's see this mathematically from the equation by itself. So we saw, and we did this quick derivation on the previous slide, that dRdt, right, the number of recovered people as a function of time, can be expressed through the number of recovered people, right, by this equation. And S0 is initial number of susceptible people. So initially, it's pretty much the entire population. And it's also clear that, it doesn't really matter whether we're looking at this picture or this picture. Right here, eventually, the number of recovered people stop changing with time, right? It's kind of flattens the tail. And if I look here, it's the same situation, right? When the time is long enough, we're going to get this flat tail. And if it's flat, the derivative is equal to 0. So why do I care? Why do we care? Well, because of this equation. So I want to understand, since I cannot solve exactly, I want to try to do some limiting behavior. And I want to look at the limit time goes to infinity. So after a long, long time, we just saw that after a long, long time, R, the ratio of recovered people stays constant, and a derivative, is equal to 0. It's not changing. So then at time equal to infinity, I can equate this to 0, and then I can rewrite this equation. Now, we can also assume at the very beginning that we had a very, very small infection, and so majority of people were susceptible, and so we can equate this approximately to 1. Then we get this equation. Now, and R infinity, we don't know. That's what actually I want to understand. I want to understand, depending on beta and gamma, what happens with the ratio of infected people when time goes to infinity. So this equation looks very simple. Unfortunately, again, you cannot solve this analytically. This is one of those equations you cannot solve it analytically, but we can actually go back to sort of probably high school or beginning of college, when we tried to solve those type of equations graphically, right? In fact, I don't want to solve the equation graphically, but what I want to do is I want to understand the following situation. I want to understand when we get this type of scenarios, when we get this blue line almost getting close to 1, right? When it is large and constant. And when do we have a situation when the blue line is kind of close to 0, right? So whether we get the situation when a lot of people got sick, or when there is just some number of people got sick, and then kind of life stabilized. So back to this equation. This is our equation, right? And I again introduced this notion of R0, which is beta over gamma. We already kind of introduced this variable before. So that's our equation. Now, the way to analyze this is the following. There is one solution for this equation, which is, and the solution in terms of like R, R infinity. What is R infinity? One solution, one value of R infinity that is obvious. So what solution what solution does this equation always have? It doesn't matter what R0 is.
0.
Yeah, so R infinity equal to 0. There is always a solution, because if I put here 0, R infinity is 0, e to the power 0 becomes 1, 1 minus 1 is 0. So there is always a solution, right? Now, the way to analyze this is we can actually think about it the following way. Let's draw two lines. One is going to be y equal R infinity, and the second line will be y equal 1 minus e to this power. Now, this axis is R infinity, this is y axis. So the solution, if we have solution for this equation, you know, it's an intersection of these two curves. I call it y1 and y2, right? When they're equal, that's a solution. So we just agreed that there is clearly a solution right here, which is R infinity equal to 0. That's always present. But then look at the shape of this line. This is, you know, there is this shape. And, you know, here it's called C, but this is our R naught. Depending on this R naught, this line have different shapes. It can go either here, or for example, it can go here. And if it goes this way, there is a place where it intersects with our curve, right, with our straight line. If it goes this way, there is no intersection. But if it goes this way, there is an intersection. So how do we distinguish those two behaviors, this behavior versus that behavior? We can actually differentiate them by looking at the angle that curves have at origin, right? So if the angle is below 45 degrees, it will never cross the diagonal line. If it is above, it will. Which condition is sort of boundary condition here? That changes the behavior, right? From no crossing to this crossing. It is when the angle, when the slope of this line, the slope of this line is 1, right? It is equal to the slope of this one. How do I determine the slope of the line? Well, very easily, right? I just differentiate it and put it at 0. And if we take derivative and put it at 0, well, we realize that this critical point is R0 equal to 1. So if R0 is less than 1, we have this behavior of the right-hand side. If R0 greater than 1, we have this behavior. When we have this behavior, there is only one solution that this equation has, and it is 0. When we have this behavior, there are two solutions it has. It has this solution and it has this solution. Now, to remind you what the solution means, solution is R infinity. It's a fraction of population that eventually is infected. And so what it means is there are two scenarios, right? There's one scenario where the final population is very small, is negligible, or the other one when it is, you know, getting infected in significant numbers, and the threshold for this behavior is R0 equal to 1. Before it, there is almost no infections. After it, rapidly covers the entire population. Now, this is sort of classical kind of phase transition type of picture. And again, guys, notice that this is the same R0. We kind of got this threshold performance, you know, on our first slide of this lecture when we looked at the, you know, branching process model. But now, you know, it sort of comes out from the differential equations that just tells you that the solution has two different behaviors. And literally what it means, it's called an epidemic threshold. And so when R0 is greater than 1 or beta is greater than gamma, we got, you know, we got an epidemics and we got finite number of infected people. And so it can go to some constant, it can go to, you know, it can go to 1 or maybe not necessarily 1. but some sort of finite number. And when no epidemics, then it kind of stays very, very low. Again, just reminding you from numerical simulation, it is this scenario versus this scenario. Here we get almost all population. Here, the blue line stays low. And the difference is that here, this is R naught epidemic threshold. This is 0.5. And on the previous slide, here R0 is equal to 4. So this is clearly greater than 1. And we got an epidemics. So we got this hump, and you know, we have almost all the people, you know, eventually get infected, versus this scenario where now this is R naught is less than 1, and there is no hump. It just slowly goes down, and we get some finite but not very large number of people who got sick. So these are kind of two different behaviors, and they being distinguished through this epidemic threshold. And so this R naught, that's why, you know, R naught is so critical, so important. It's called also basic reproductive number, basic reproduction number, the ratio of recovery rate to infection rate, or ratio of recovery time to the time then during which infection happens. So, you know, that again, R naught can also be interpreted very easily from this model as an average number of people infected by a person before his or her recovery. Okay, so to sum up, these are sort of three basic compartmental models: SI, SIS, and SIR. Here, what we color code is the number of, it's always number of infected people. This is number of infected people. And that's the behavior of the models. When we have SI model, eventually everybody gets infected. When we have SIS model, there is some fraction of population that is infected, and this fraction stays constant. Now people can recover and then get sick again. It's not the particular person that always sick. It is just, you know, there is sort of rotation of people who getting sick and get recovered, but the fraction of the population that is sick at any present time remains the same. And SIR model, where you got this hump, where you got the wave, and then you know, it drops down simply because people get immune or die. For SI model, there is no threshold. It always happens. For SIS and SIR model, remember, we could get either this type of behavior or like almost very, very flat behavior if the disease does not cross this threshold. And another important point is the beginning. If you notice, pretty much all of these models at early time have exponential shape here, and the exponent in SI model is just beta. In SIS, SIR is beta minus gamma. It kind of coincides here, beta minus gamma, that determines the growth. And so that's the exponential growth. That's what we observed on the slides at the beginning of the lecture. That's what we observed at the beginning of the epidemics. That's what we observe on every wave. And by the way, it looks like the third wave is coming, and we are somewhere here now. Okay, so these are models that were introduced in 20s, right? 27. Of course, since then there has been, you know, a lot of models introduced to describe very specific, you know, types of diseases. You know, within last year, there's been a great, you know, huge renewed interest in this type of modeling by obvious reason. Just want to show you a couple models that you can actually build based on the same approaches. So one of those models, it's called SI, and by the way, the models are called based on those letters, right? So SIRS, so it is sort of our SIR model, right? This SIR model, but then from recovered after some time, you can get susceptible again. And for COVID, it looks like that's what it's going to be, right? The antibodies goes away, so you can probably need to do this. Now, again, speaking of COVID, there is definitely a better model that describes COVID because we have susceptible, we have exposed people. So those people who carry the infection, but they don't have any symptoms, and it's usually with COVID it's like 5 days. So you get symptoms only after 5 days, but you're already exposed to infection, so you're already carrying the infection, and the person might be infectious but with less rate. And then there is infectious stage, and then can be recovery. So it's called SEIR model or SEIRS model if we allow going back. And notice there is just we adding more parameters, but in fact it just means we'll add more equations, right? And it's sort of more groups of people, right? More blocks. Then there are, for example, modification of the models. It's very clear from COVID again that people, depending on their age, for example, or their overall health, gender, some of the people are more vulnerable than others to the disease. And for example, one of the proposed models takes that into account and splitting, population into compartments: exposed and then vulnerable. Exposed, again, this can be age splitting or gender or overall health status splitting. And then, different, then there is infectious, and then, the outcome, it's actually can be either recovered or people can die. And depending on the sort of, on the path, there are different coefficients that determines those transitions. Now, those coefficients, they can be determined from the observations from the data, right? Finally, I want to show you one more model, which is probably, at this moment, the most used model. It's again named by the letters. So we start with susceptible people, then we get exposed people, right? Those that got exposed. And there's this, of course, transition rates. Then based on the behavior of the disease, there are some people becoming asymptomatic, and by whatever reason I cannot draw again. They're asymptomatic, and then they easily recover, and that's done. Or alternative option is a person becomes symptomatic and then is hospitalized. Probably something happened. So asymptomatic and then recovers, or a person can become symptomatic and then either stay at home and recover, or being hospitalized to ICU unit. Even within the hospital, his personal condition can change. And then, if he recovers, then goes to recovery, or unfortunately people die from any of those locations. So this is really this 8 compartments that describe in detail, a journey of somebody who gets sick with COVID. And then, if you want, some people introduce on top of it again this age compartments, etc., etc. But the point is, for each of those transitions, there are coefficients, right? There is this, you can call it beta, beta 1, beta 2, beta 3, etc., etc. So for each of the transitions or coefficients, those coefficients can be obtained from the statistics, from the observed statistics for real patients. And then one can simulate this model. Now, and then, for example, you can predict from this more precisely how many beds you need in the hospital, how many beds you need in ICU units, and sort of overall expectations of the outcome for the population. But interestingly enough, and I don't have pictures here on embedded in this presentation, but you can look them up in the paper. The model can have a lot of transitions like that, but ultimately, the performance of this, infected asymptomatic or infected symptomatic in all cases is described by those humps, by the wave, and then it goes down. Now, one more thing which is important, notice that if we're solving differential equations, we have this R0, it can be actually a function of time when we do the simulations. And so R0, remember, it's the ratio of, in a basic scenario of the transmission over recovery. And so this transmission rate can be controlled by modifying our behavior. So for example, wearing masks drop that rate, or introducing lockdown drops that rate significantly. And in fact, you can put this behavior into the model, right? And when you do integration, then you get very different behavior. Say, for example, if at some time t0 you get the lockdown, you will get a very different behavior, dropping rapidly this hump. And so that pretty much what happened in many countries when they introduced lockdown. So bottom line, the models that has been developed, by Kermack and McKendrick, in 1927 became extremely useful now, which is, 100 years later. Yes, they've been expanded. Yes, there are, various attempts to take those models and add on things to them like machine learning, deep learning, sort of autoregression, but the basics still stay there. Next lecture, we will actually modify these models to work on the networks. And that's why I wanted to spend this time to learn about the differential equations. Next time, we'll look what network does, what network effects we're going to see, and how we actually, with a network model, we actually can observe multiple waves of infection. And that's it for today. Questions? All right, so no questions. Thank you very much, guys, and see you next week.